Okay, so this is the 16.3 notes for statistics honors. In the previous lesson, in 16.1, 16.2, we talked about how to use the F distribution table, as well as some of the logic behind the ANOVA. This lesson will pretty much bring it all together, and we'll be running some tests to make sure something is, or to verify if something is significant or not. So first things first, we already calculated F prior to this, so you know that it's equal to MSTR over MSE. The one thing that you do not know is how to calculate the degrees of freedom. So here's your calculation. Remember, we use parentheses with a comma since there are 2 degrees of freedom for an F distribution. So first formula, degrees of freedom numerator is always going to be equal to k minus 1. Remember, k is the number of populations in our scenario, and the degrees of freedom denominator is always going to be equal to n minus k. So k is obviously still the number of populations, but n represents the total number of samples that we took. So obviously you have to know the degrees of freedom in order to make these judgments, so make sure that you are very clear on how to do that. Just as a little bit of a review here, remember that when we talked about ANOVA, we used the SSTR to compute the MSTR, which was all about measuring the variation among the sample means. Then we used the SSE right here to calculate the MSE, and that was all about measuring the variation within the sample. The goal, of course, is to measure the ratio of this, of the among the sample means to within the sample to get your F. Obviously, that is not, it makes sense that not all students are going to quite understand like the concept there, but the key is it's all a mathematical computation. So as long as you understand that F is a test statistic and you can measure it against a critical value or find a p-value, that's all that really matters in terms of the class and moving on. So a new concept here, not super in terms of like complicated or anything like that, but it makes sense though that if we have variation coming from 2 different places, that we might want a look at the total variation. So we call that the total sum of squares, which is SST. So basically, SST is going to be equal to SSTR plus SSE. Okay, so there's also a formula for calculating SST, and it is here. So if you took each individual x and subtracted the grand mean x bar bar, then squared them and added them all together, you would get the total sum of squares. So I'm going to sort of go back and forth here, but what the key is what you want to do is you want to look at this right here. So the formulas that you already learned are here and here. So in the previous section, we calculated SSTR by doing the sum of all n times the sample means minus the grand mean squared. And in the prior section, we did the error is going to be the sum of all the sample sizes minus 1 times the variances. So this is something that we've accomplished already without an issue. So the new concept is actually here. So you might say, well, why do we actually need to know this? Are you ever going to be asked for this? Well, hypothetically, you will need to know that you'll have to fill out the sum of the SST, but it truthfully, all it is taking these two together and adding them. So technically, you don't have to calculate SST directly, but there's a big but here. So if you recall in our problem that we work with, in our example problem in the previous section, I told you, so this right here, the variance. So if you recall, I actually gave that to you. Normally, the variance is a pain in the butt because it's not something you can just calculate from easily from a table. You would have to put all the data in, find the variance using statistical software. So let's say you didn't want to do that. let's say you wanted to instead use a much easier formula here that you could use in order to use just a table to figure it out. Because if you think about it, this is just each observation, and this is just the grand mean. So that's easy to do using a table. So what I'm getting at here is, believe it or not, the standard is not the way we did it previously. It's not taking these two things and finding them directly. It's actually taking these two, finding them with a table, and then subtracting SST minus SSTR to find the error. So it's worth noting in these scenarios that knowing all three formulas is obviously usable, and we're going to be going through and applying this in this section. Okay, so we basically have all of these really these statistical calculations already that we found with ANOVA, but it's hard to really keep track of them. I mean, we have some degrees of freedom, we have some SSTR, SSE, MSTR, MSC, we have F, we have all of these. We even have this new calculation, SST. We have all of these numerous things. So what statisticians eventually did was they came up with something called an ANOVA table as a way to collect all of this information in one place. So what you'll find is if you went into statistical software and started running an ANOVA test, it'll basically just spit out an ANOVA table, a table filled with all of the calculations that you're doing by hand right now, but the statistical software would do it for you. So what I did was I gave you the ANOVA table with all of the formulas in them. So just a small thing here. So you'll see that this is the degrees of freedom column. You have the treatment row and the error row. So in the treatment row, this is going to be the degrees of freedom numerator, which we said was k minus 1. In the error row, it's going to be degrees of freedom denominator, which is n minus k. You'll see that all the familiar values that we calculated are all here. They also have the formulas associated with them. I figured I'd throw them in there just to make life easier for you in terms of going through it. But another important concept here is the DF and the SS column, sum of squares column, also add straight down in order to create your total sum of squares and its degrees of freedom, which is n minus 1, which is your more typical degrees of freedom. Now, that's the first thing. So everything that we calculate, we can summarize in a table, which I'll show you in 1 second. Now, one thing to point out here, though. If you look at this table, there's a lot of logic to it. So if you see here, we start with k minus 1 and SSTR. Well, when you calculate MSTR, you actually take this value, SSTR, and you divide this value, k minus 1. So literally, in order to find this row, or this column, all you have to do is divide the previous two things divided by one another. Let's see if that's the same down here. So you have n minus k, you have SSE. It looks like MSE is going to be equal, again, to dividing those two values. So basically the chart is pretty neat in the sense that you can actually use values before it in order to calculate. And that continues again because you guys know that F is taking these two and dividing them. So the entire table itself is just taking a bunch of values previously, so you can fill it out from left to right very easily. Alright, so let's see how this thing is filled out. So we're going to go back to the energy consumption problem that we talked about in the previous section and start filling some of this out. So just as a reminder, I'm going to go back to that lesson. So if you recall, we actually calculated a bunch of these things. So for example, F right here was 6.32. We have MSC is 5.581. We have MSTR is 35.3. We also have SSE and N minus K here, which are 89.3 and 16. We also have SSTR and K minus 1, which are 105.9 and 3. those, believe it or not, are all the values that are actually in the table. So if we fill it out from how we calculated it, our test statistic was 6.32. Our MS values were 35.3, 5.581. Our SS values were 105.9 and 89.3. Our values of K minus 1, so just a reminder, so this is K minus 1 right here. We're going to go right there. So K minus 1 is 4 minus 1, which is 3. Remember, this was N minus K, which is here. So that's going to be 20 minus 4, which is 16. And then the only thing left to do is add straight down in these two columns to get 19, which is actually N minus 1. And the sum of squares, 195.2. So note that this value, we did not calculate that directly using this formula. All we did was add the two sources of variation together when we did that. So basically, what does that look like? If you look at this whole thing here, right? This is the ANOVA table. This is the output that statistical software would output. This is something that you would provide to me on an exam situation in most semesters. So literally, this is the most important part of an ANOVA problem, besides the conclusion, of course, is producing this table. Okay, a lot of it will require that you do hand calculations in order to do so as well, but this is the big concept that is involved when it comes to an ANOVA test. Okay, so last thing here is, I'm just going to read through this so that you can get an idea of where we're going with this here. It says, as an aside, just realize that the table is quite user-friendly, because if you're given certain elements of the table, you should be able to find all the others utilizing the formulas and a little algebra. Okay, so what does that mean? So if you look at our ANOVA table right here, it's all just formulas, which means if I gave you different values in here, like if I gave you this one, and this one, you should be able to take that and find the rest of them using all of these very simple mini formulas that are here. So look at this problem, for example. So you can see that I'm provided these values right here. So I claim that you should be able to go through these values and find all the rest of the ones that are missing. Okay, that is the key concept involved with this. Is that, and it's very useful because it gets you using the formulas and understanding how they work. Okay, for example, if you look here at the first row, we talked about how each one of these values is used to find the next one in the list, right? So if you go back and look at the formulas that are up here, what did we say? We said that this value here, this value, is the equivalent of taking this divided by this. So what that means exactly is that we should be able to work backwards in order to figure out missing pieces. So for example, we know that, just as our setup here, we know that 0.708 was found by taking 2.124 and dividing by whatever this is. Okay, we'll just say df. So that means we should be able to do a little bit of algebra here in order to figure out what the missing piece is. So for example, if you cross-multiplied in this, so if we put this over 1 and cross-multiplied, we would get 0.708 times df is equal to 2.124, which means df is equal to 2.124 divided by 0.708. Well, believe it or not, that's actually equal to a perfect 3, which means the degrees of freedom for our treatment is actually 3. So if you look at this real close, now just note, that is the equivalent to k minus 1, which is the denominator. We abbreviated df to make life a little bit easier, but that is your k minus 1 value. Well, once you get one of these values, then there's sort of a chain reaction. So for example, we now know both of these degrees of freedom, which means the total degrees of freedom for our problem is going to be 23. Okay, so what's next? Well, it looks like the first row is good, but we really don't have anything in the second row. So there might be a new strategy to figuring this out. So let's return to the F statistic. So we're actually provided that in our problem here. So remember that your F statistic in our problem, so F right here, is actually equivalent to this divided by this. So that provides another avenue for what we can do here. So we can go over to the F statistic and go, well, 0.75 is actually equal to this 0.708 divided by this value here. So that value is actually called MSE. So just as a reminder, it's called MSE. So we'll leave it there. So again, we're in algebra world. So if we, let's say, cross multiply, we get 0.75 MSE is equal to 0.708. So that means my MSE is going to be equal to 0.708 over 0.75. If you do this calculation, you're going to get approximately 0.944. So we throw that right in there. 0.944. Let me get. And we found MSE. Okay, and lastly, we only have one more missing piece of information. It's technically the SSE. So let me get rid of the noise here. Okay. So it's SSE is our missing piece. So right now, in our problem, we actually have this and this. So we know that MSE is equal to this divided by this, which means, again, we should be able to use a formula here where we go 0.944, which is MSE, is equal to our SSE, our blank, divided by 20. So if we multiplied 20 by both sides, we're going to get an SSE equal to 18.88, which goes right here. So that is our sum of squares error, and of course the chain reaction, the last step, is we can add these two together and get 21.004 as a result. So you're not going to be doing this a lot, but I find that this type of exercise, which you might see in your homework, is excellent for understanding the formulas and how each one of these values in the table relate to one another. All it is a mini algebra fest. Students sometimes struggle with it because they don't quite know the formulas in the beginning, but once you get used to it, it's pretty quick to figuring out. It has really nothing to do with the actual ANOVA test itself, but again, it's very good at getting you to really hunker down and understand what each one of these formulas is and how they relate to one another. Okay, so now let's take a look at the entire ANOVA test on one page, so you can really absorb it. We've talked a lot about it already, obviously, but let's do that. And then on the next page, we're going to actually make a decision on our home energy consumption problem, so that you can really get a look at what this ANOVA test, what it can do. Okay, so recall that our assumptions were similar to a two-sample T. So we're looking at independent random samples. We need normal populations for all of your populations. So that means ideally they're all bigger than 30, or there's a statement of normality provided. Sometimes you also will have to do normal probability plots for each one. And the last thing is we want approximately equal standard deviations that we're managing for this. Okay, so last time we talked about the null and alternative. So remember the null is always a statement of equality. So it's basically going to be mu1 equals mu2 ... equals mu to how many populations you have. So we're going to talk about it in a second, but if you remember from our previous problem, our home consumption, there was 4, so you're going to go up to mu4. Our alternative is always just going to be the statement, not all the means are equal. We're going to need an alpha. We're going to compute our test statistic, which was MSTR over MSC, and we're going to do there's going to be a very large calculation in order to do so. Before you even provide that, the goal is you will always show an ANOVA table with all of your calculations in it. So it's going to be a lot different than what you're used to. Even though you are doing calculations, you're using the calculator to help out. Whereas with the ANOVA, you're really going to be having to do a lot more hand calculations to figure this out, and a lot more places for error or errors to make. And then, of course, we return to our two approaches. I'm going to show you both of them so that you are schooled in understanding them. So just remember, the only thing that ever changes in these approaches is the degrees of freedom. So remember, the degrees of freedom in this is k minus 1, n minus k for DFN and DFD. One small thing other than that is remember that these distributions are skewed. Specifically, they are skewed right. So the tail is always going to be on the right. So there's going to be some fine tuning when it comes to actually doing the p-value in the calculator and a bunch of other things, which we'll talk about when we make the conclusion. Okay, so returning to our energy consumption problem that we talked about. So we've already done this, the null and alternative hypothesis. So you want to absorb that. Remember, this is the data that we talked about in the previous lesson. Earlier in this lesson, I filled out the ANOVA table. So now we have that. So the key is, if you have this ANOVA table, as with all the results we need, can you use the critical value and p-value approach in order to make a decision for this problem? So what we're going to do is we're literally just going to do that. We're going to go through and we're going to use these approaches and make sure that you know what you're doing with them. So for example, the critical value approach. So some of the things that are of importance with this, well, we need to know alpha. So alpha was 0.05 in this problem. We need to know degrees of freedom numerator. So degrees of freedom numerator is right here, 3. We need to know degrees of freedom denominator, which is right here, 16. Okay, just remember that those are found using k minus 1 and n minus k. So you remember, right? So we need to use that in order to find our F critical value. So again, what's going to happen? We're going to end up with a value, some value of F, that's going to mark our non-rejection and our rejection region. What do we always do in the tail? We always reject H0. What do we always do elsewhere? We do not reject. There's no such thing as a two-tailed test anymore. Essentially, every test is a right-tailed test. That's the best way to think about it, because in the skewed distribution, the tail is always on the right side. So how do we find this value? So just as a reminder, we're looking for df is equal to 3, 16 at alpha equals 0.05. So this will be good practice for you. So we're going to go over to the F table, right? So if we go over to the F table, we're looking at 3, but if you look at for numerator, but for denominator, it only goes to 8. So that means this isn't it. So we go to the next one. You'll see that the top values don't have a 3, so that ain't it. We go here and we go, okay, we have a 3. Now let's see if we have a 16. Oh, we do, 16. Okay, so 3 and 16. So we're basically dealing with one of these 5 values. Well, which one is it? Well, alpha is 0.05, so that means we're dealing with that value right there. So 3.24 is going to be our critical value for this test. So F of 0.05 is 3.24. So what do? We take our test statistic, F, and we place it, as we normally do, in our chart. So this is actually going to be about right there, 6.32. Which means we are in the rejection region, and we therefore reject H0. So again, what does that mean? So reject H0 means that we're tossing the possibility that all of these, hold on a second, we're tossing the possibility that the means in all the regions for energy consumption are the same, and we're saying at least one of the two of the means differ from one another. So could it be South and West Shore? Could it be Midwest and West Shore? But we don't know that yet. We will be able to determine that in a second, or in the next section. But for now, we reject the null and say that energy consumption is not the same for the 4 populations that we actually have. Okay, so what about the p-value approach? Well, we're going to be using, instead of using crazy, using intervals that we did for p-value, we're going to go right into using the calculator. So if you go into the normal area on your calculator, which is, I believe, distribution. Let me just check for a second. Yep. So if you go to second vars, which is distribution, you're going to find a command called fcdf. So your fcdf command is essentially going to be set up as follows. So you're going to put your lower band. The lower band is always going to be your value of f, your f statistic. Why? Because your f statistic is always going to be, so in this problem it's 6.32, it's always going to be the left side of your tail region. Your next value is always going to be 1E99. Why? Because that's always the upper bound. No matter what, the upper bound is always the highest number you can think of, essentially. The last 2 numbers are going to be DFN and DFD. It's going to be very straightforward. So in order to find this area right here, what are we going to do? We're going to do FCDF of our lower bound 6.32. Our upper bound is always 1E99, and then 3, 16. If you throw that into the calculator, you're going to get approximately 0.0049 as your p-value for this test. And if you recall, our alpha is 0.05, so since p equal 0.0049 is less than alpha 0.05, we again reject H naught. So this confirms our previous conclusion for our scenario here. So both methods need to be known, but in this, you just got to make sure that you can make this conclusion in the end. The one thing about ANOVA problems is that the actual problem could be presented to you in a couple different ways. So for our energy consumption problem here, I meant to have the eraser out. For the energy consumption problem, we basically have all the regions and the data in each region, right? So that is a very common way for an ANOVA problem to be provided to you. But there is another way that I've seen in which the actual ANOVA problem could be presented to you. So I'm just going to read it and then talk about how it's presented. It says a study is done to compare the birth weights in pounds of newborn infants based on the smoking behavior of their mothers. At the 1% significance level, does it appear that a difference exists in the mean birth weight amongst women and their smoking habits? The data is shown below. Okay, so note, if you look here at this is the only thing that is given to you. Notice that there is no data. So here, the individual data values were provided. Now, instead of that, they're giving you not the data, but the number in each sample. So there are 6 non-smokers, 5 X, and 7 smokers. They're giving you the mean birth weight for each of the categories and the standard deviation of the birth weight for each of the categories. So the key is understanding that this is an alternate way for this to be provided. You will be asked to also do this in your homework, so you want to be schooled in running with either type of scenario that is provided to you. And on the lab in this section, you'll have to also do both scenarios. So be ready for that when you're doing any type of ANOVA problem. Okay, so let's get down to the calculations. I know there's some info here. I'm going to get to that in 1 second. I'd rather do that in the flow of things. So let's talk about this null and alternative hypothesis. So just to be clear with what we're dealing with here, essentially all the values, all the statistics in this problem are about the birth weight of a child. But the factor that they're measuring this with is the smoking behavior, which has 3 levels. Okay, those 3 levels are non-smoker, ex-smoker, and smoker. So essentially, if we're going to make a null hypothesis, we know it's a statement of equality of 3 populations. Non-smoking, ex-smoking, and smoking population. Okay? The alternative is always the same. It's not all means are equal. Okay, so in the scope of our test, we have the null and alternative. In reality, if we move back real quick to our test that we have to run, note it does say assume conditions are satisfied, and I often do that in these tests, but they're very easy to figure out. But I'm just going to try to those stuff I know you know how to do. I'm just trying to get through the test itself. But we already took care of the null and alternative. Alpha in this problem, I don't think it's listed. Oh, it is listed. It's 1%. So all we have to do is find F now, which is this entire table. So we have to go through the process of figuring out that table. So remember, SSTR and SSE have their own unique large table, calculation tables associated with them. So this is quite the undertaking, that is for sure, but that is going to be the goal. So what are we doing essentially? So let me just remind everybody. So if we go back to our previous lesson, if you recall, we had to create an SSTR and an SSE calculation table in order to figure out what those values were. That is what we have to do now. So returning to our problem, here we are. Let's go through the table. So the first thing is we have to create an SSTR table. So what does that look like? Well, we're going to do non-smoker, ex-smoker, and smoker as my categories. And for that table, this is going to be a review. That is an awful line, by the way. I'm going to do, we need n. We also need the mean. So we're going to call that x bar. We'll get to the rest later. So what were our values? Well, our n's are 6, 5, and 7. Our x bars for each of them are these values. So 7.58, 7.24, 6.15. Okay, so if you recall, the formula for SSTR required that we find all our individual means minus our grand mean, x bar bar. Okay, so you'll notice that we don't have our grand mean. Okay, that's where this comes in over here. So our grand mean is missing. We don't know what that is. It wasn't provided or anything like that, so we have to find it. Now, the grand mean, if you recall, in the previous problem, we actually added every individual value, all of them, added them all up and divided by how many there were. Well, now that we don't have the actual data, we can't do that. We also know that we can't take the average of these 3 values because the sample sizes are different for each one. So therefore, we actually have to come up with a new way to do this. So what is the way to do it? Well, the idea is you have to undo mean in a sense. So whenever you calculate the mean of something, what do? You find the sum of it, all the values, and divide by n. Well, what we need to do is we need to find the sum of the values, which means all we have to do is multiply both sides by n. So, but what is that doing? That's taking the average times n. But look, this is the average times n. So what do we have to do is we have to do the n times the mean for each one. So here's the first one. So if we want to find x bar bar, our grand mean, we first do 6 times 7.58, then 5 times 7.24, then 7 times 6.15, and then we add them all together. Hopefully you understand that if we do this calculation here, we are going to get the sum of all the individual x's in our problem. That is the goal for what we would do here. And what do we normally divide by? We divide by how many there are. Well, what is that value? It's taking 6, 5, and 7 and adding them together on the bottom, which is essentially our n. If we do that, we're basically doing this, but we're doing it in a backwards way. So what happens when we do this calculation? We get 6.93. Okay, so what do we have to do? So we're going to be taking 6.93 here. We're going to take all of these values right here, and we're going to be subtracting 6.93. So what do we get? We get 0.65, we get 0.31, and negative 0.78. Okay, these are our values for each individual mean minus the grand mean. So again, returning to the formula that we needed for SSTR, it was actually the sum of all of the nk's times x bar k's minus x bar bar squared. So that was your formula for SSTR. So far we actually have what's in here, and we have n, but we have to now square what's here. So this is going to be x, all the individual x bar minus x bar bars, which we have already, squared. So what happens if we square this column right here? Well, let's do it. We're going to get 0.4225, 0.0961, 0.6084. All right, so if we have all of that, the last step is finding the formula. The formula is taking, let me just highlight it, it's taking this column and this column and multiplying them together. So n times x bar I minus x bar bar squared. So our first value is 6 times 0.4225, which is going to give us 2.5350. So just to be clear, this is 6 times 0.4225. Our next value is going to be 0.4805. We get this by multiplying 5 times 0.0961. And our last value is 7 times 0.6084, which is 4.2588. So again, 7 times 0.6084. Okay, so what was the point of all of this? Well, you've already done this before, so hopefully this is understood. So the value that you get is SSTR, which is the sum of this column, which is 7.2743. So the whole point of obviously the SSTR table is to find the SSTR value, which is 7.2743. Okay, so if you recall, the whole point of SSTR is to find MSTR. Well, MSTR is equal to SSTR divided by K minus 1. Alright, so SSTR is 7.2743, rounded to 4 decimal places to make sure that we have as little error as possible. And now we have to find K minus 1. So remember, K is the number of populations. So if we go back to our problem, how many populations are there? There are 3. So 3 minus 1, and then this will give us approximately 3.63715. I went to 5. You can go to 2 decimal places. It's not a big deal. Just do at least 4 so that you get a much the error. So essentially, this is our next key value. Remember, this is the numerator of the F statistic. So essentially, we are halfway there, right? We're halfway there. I know that sounds crazy. We did all this work and we're only halfway, but that is what's going on here. So what do we do next? We have to find the SSE table. So just a reminder, the SSE was basically n minus 1, the sum of nk minus 1 times the variance of our problem. So what do? We create another table of non-ex-smoker. Okay, and that, let me try to get straight here. There we go. So what do we need? We need an n. We already know that 6, 5, and 7. We also need a variance. Okay, so that's s squared. Well, we're kind of lucky in this problem in the sense that, look at what we're given. We're given the standard deviation, and everybody should know that all we have to do is square the standard deviation to get the resulting value. So the first value is, again, it's 1.05. So when you square 1.05, you get 1.1025. I'm going to write an arrow here. So this is 1.05 squared, right? So then the next value squared is going to be 0.92. So we're going to, if we square 0.92, we're going to get 0.8464. So just a little bit of an arrow here. So this is going to be 0.92 squared. Okay, and the last value is going to be 0.9604, which is going to be 0.98 squared. Okay, so we got all our variances. So the only thing left to do, we have n and we have the variance, so we just need n minus 1. So we're going to do n minus 1 here, which is just 5, 4, and 6. So last column is what we need. So we need n minus 1. We don't need the k there. It's technically k, but so we don't get confused. And then s squared. So we're going to do basically our this column times this column. So it's going to be 1.1025 times 5. Oh, actually, you know what? Let's just do the whole thing. I'm going to do it like I've been doing it. So what is this? First of all, this value is going to be 5.5125. How did I get it? I got it by doing 5 times 1.1025. Next value is going to be 3.3856, which I get by multiplying 4 times 0.8464. Last value is going to be 5.7624, which I get by multiplying 6 times 0.9604. Okay, what is our goal again? We need the sum. So SSE is going to be the sum of this column, which is going to give you 14.6605. Okay, so what was the goal of this? It was to find MSE. What is MSE equal to? It's equal to SSE divided by n minus k. So we already know what this is, 14.6605. We calculated it. So remember that we are subtracting k here, which is 3, but what is n? N is the total number of samples, so remember that is here actually. So that is the sum of these numbers 6, 5, and 7. So that's going to be, it looks like 6, 5, and 7 make 18, right? 18. So we're going to get 18 minus 3, which is 15. So when we do this division, we're going to get 0.9774 for MSE. So once you get these two, then you have that one more step to fill out, and that's to find F. F is equal to our MSTR over our MSE, which is going to be equal to 3.63715 over 0.9774, which is approximately 3.72. Okay, once we have all these calculations, we basically have to fill out the ANOVA table. So that's next. We have to get all of these in a nice place to fill out. So here's our ANOVA table. And then we have to make our decision on our actual test. So obviously one of the longer tests that you'll run, but it is what it is. You have to go through the calculations basically for this. So filling everything out. So first of all, our F. So that was 3.72. What were our MS values? They were here and here. So we have 3.63715 and we have 0.9774. Okay, what about our SS values? They are here and here. So 7-ish and 14-ish. So 7.2743 and 14.6605. What about our degrees of freedom? Okay, so for this, Our degrees of freedom, believe it or not, we didn't do it, we didn't actually do it by saying it, but we did it in our calculations. They're here and here. So what were they? They were 2 and 15. So 2 and 15. So the only thing left to is to add straight down. We get 17 and 21.9348 for our ANOVA. So this is our ANOVA table. This would be provided. You would need to provide this as a summary. It's also very easy for me to grade as well, because if there's one, usually if one row is messed up, then the rest of it's going to be messed up, like one part of a row. So I can then backtrack and check your work and so forth. Okay, once again, it's all about making decisions. So we're going to do both methods. So CV method, p-value method, critical value and p-value, right? So we're going to use both methods for practice. I'm going to use a different picture for each. So here we go. Let's do a typical skewed distribution. So what is our goal? We need it for a critical value method. We need to find the F statistic, not the F critical value, which is the cutoff. So just a small thing here. Remember, this was at the 1% significance level. So we're trying to find F sub 0.01 at degrees of freedom equal to, we'll go up here, 2 and 15. 215, right? So what would you do, as we've been doing? You would go to your F table, right? And luckily we actually are on the page that we're going to need here, because if you remember, we were finding 3 and 16, so 2 and 15 are going to be on the same one. So 2 and 15 would be 2 here, 15 here, which means we want this group of numbers, and we're looking at 0.01, which is going to be 6.36. So we need, go back here. So this value here is going to be 6.36. This is going to mark the difference between rejection in the tail and do not reject everywhere else. So what do we do? As we always do, we take our 3.72 and we place it where it belongs. It looks like 3.72 is our F statistic is somewhere over here. So that is in the do not reject region. So that's what we write. Do not reject. H naught. So just to be clear here, what does that mean in the scope of our problem? Remember, this was all about birth weights for smoking versus non-smoking. So the mean was that they were all the same, and the alternative was that they weren't. Well, we did not reject H naught, so this is implying that the mean birth weight of babies is the same for all of the 3 smoking groups based on our statistical analysis. So that is going to be the key conclusion that we're actually doing here. Now, what about p-value? So again, we use a different picture usually. So let's draw another one. Here's our skew. So this time we actually put the test statistic, F equals 3.72, on the table, and our p-value is to the right of it. So we use FCDF. So we're going to do FCDF of our test statistic F. We always are going all the way out to the biggest number in a right skew distribution, and then our degrees of freedom are 2 and 15. If we do this calculation, we're going to get 0.0488 as our p-value. So remember, we are at alpha equals 0.01, so we basically, since p equals 0.0488 is not less than alpha 0.01, we do not reject H naught. Okay, so same conclusion for both. That's obviously really important because it's just an alternate way of doing it. But this is the test. This is how it's done. I gave you an example of each. Obviously, it's a very long process, so you shouldn't really need to go through a bunch of examples in class. The key is going and doing the homework and making sure that you can sort out how to calculate all these crazy ANOVA table and all these individual statistical values like SSTR and all that stuff, using tables and manipulating them to make them work. But that is essentially what this entire process is about. So, uh, lots and lots of studying when it comes to this, lots and lots of practice. That's the best way to get it.